Good evening. My name is Carol Christ, and as Chancellor of the University of California at Berkeley, I have the great pleasure of welcoming you to tonight's Breakthrough Prize panel discussion, which explores some of the biggest and thorniest questions in the basic sciences. I'd like to thank the Breakthrough Prize Foundation for bringing together such an esteemed group of panelists and a wonderful audience of scientists and science enthusiasts here at Berkeley. Ours is a campus with an incredible research legacy. E.O. Lawrence's first experiments with the cyclotron, which helped us discover the fundamental structure of matter, were held just east of where we now sit, across from the Greek Theater. Down the road in Gilman Hall, Glenn Seaborg discovered plutonium 78 years ago. More recently, this campus saw Breakthrough Prize laureates Saul Perlmutter, Jennifer Doudna, and Ian Agol all conduct groundbreaking work that upended traditional thinking within their disciplines and has had ripple effects for all of society. UC Berkeley is also honored to play a role in the Breakthrough Listen initiative, represented this evening by Dan Wertheimer in the audience. Breakthrough Listen is the largest scientific research program aimed at finding evidence of civilizations beyond the Earth. The pursuit of new scientific knowledge feeds our sense of adventure and our passion for discovery. It also unlocks the secrets of nature, often providing insights that help us address crucial challenges, sometimes in unpredictable ways. Before we begin tonight's discussions, I'd like to thank the Breakthrough Prize sponsors and organizers for elevating and celebrating scientific inquiry, for their support of meaningful research, and for creating excitement about the pursuit of new knowledge and careers in science and technology. Our scientific strength is a treasure which we must sustain and build on for the future, and I'm so glad to have such incredible partners in these efforts. Thank you. Now I'd like to invite the university's president, Janet Napolitano, to the podium to offer remarks and introduce tonight's panelists.
Well, good evening, everyone. On behalf of the University of California, I am delighted to join UC Berkeley Chancellor Carol Christ and UCSF Executive Vice Chancellor and Provost Dan Lowenstein in welcoming you here this evening. UC Berkeley, UC San Francisco, and Stanford University, represented here tonight by Vice Provost and Dean of Research Cam Moeller, are honored to host today's Breakthrough Prize Symposium and to welcome so many distinguished laureates whose work is advancing our knowledge of our world and of ourselves. I would also like to thank the Breakthrough Prize Foundation, as well as Yuri and Julia Milner, Sergey Brin, Priscilla Chan and Mark Zuckerberg, Ma Waten and Anne Wojcicki for their investment in transformative advances in research that will benefit humanity for generations to come. Since 2013, the Breakthrough Prize and its laureates have drawn attention to the profound benefits we reap from creating new knowledge. This year's laureates are no exception. They are searching not only for answers to some of humanity's biggest questions, but also for practical solutions to the most difficult challenges our society faces. Their discoveries have major implications for the treatment of disease, the future of quantum computing, cryptography, clean energy technology, and more. And it's no accident that many of the discoveries and applications explored here today have their roots in university laboratories and classrooms. Throughout history, universities have nurtured robust interdisciplinary exploration of the universe, from nanoparticles to the largest galaxies. And in turn, visionary scientists like those honored this week have explored new fields of knowledge and developed innovations that have made all of our lives, and indeed our planet, better. Today's symposium has been a testament to the tremendous value of nurturing, celebrating, and most importantly, investing in this type of scientific inquiry, not only to reveal fundamental truths about the workings of the natural world, but also to generate new science-based technologies with the potential to further improve the human condition and the economy. Now, no one is better suited to today's conversation about the transformative potential of scientific research than the laureates themselves. So I am pleased to introduce tonight's panel discussions, which will explore some of Stephen Hawking's big questions about life, science, and time travel. As Hawking declared in an interview a few years ago, there is no aspect of reality beyond the reach of the human mind. Indeed, there has never been a more important time for us to contemplate and understand what science is telling us about our future and the challenges and opportunities that lie ahead. So please join me in welcoming Dr. Derek Muller, who you may know from his YouTube channel, Veritasium, and our first group of panelists to begin tonight's conversation. And in the words of the motto of the University of California, Fiat Lux, let there be light. Thank you.
Welcome, everyone. I'm delighted to be hosting tonight the first of these 3 panel sessions where we bring together some past and present Breakthrough Prize laureates to discuss some of the broader issues, questions, philosophical and scientific. Now, this year we are celebrating the life and work of Stephen Hawking, who was, of course, a giant of physics, a personal inspiration to me. I still remember reading A Brief History of Time in my teens. You guys as well?
Yeah.
And, you know, he was also heavily involved with the Breakthrough Prizes. He was a laureate himself. He was often involved in collaborating on the prizes, and he was part of the Breakthrough Initiatives, which are a series of space science programs investigating life in the universe and interstellar travel. Now, this fall saw the publication of his last book, which is Brief Answers to the Big Questions, and we're going to be drawing from this book for the big questions that we're taking on tonight in these 3 panel sessions. The first one that we will be taking on as a panel is time travel possible? Is it? If anyone will look at the program from today, this panel session was scheduled to run at 5:30 a.m. The answer is clearly yes, we can all go home. Just kidding. Let me read a quote from the book. This is in Stephen Hawking's own words about the question, is time travel possible? He says, I think this is an important subject for research, but one has to be careful not to be labeled a crank. No government agency could afford to be seen spending money on anything as way out as time travel. Instead, one has to use technical terms like closed time-like curves, which are just code for time travel. Yet, it is a very serious question. Since general relativity can permit time travel, does it allow it in our universe? And if not, why not? So to answer those questions, I give you some of the brightest minds on the planet. We have on the far end, Nima Arkani-Hamed. He is a professor at the Institute for Advanced Study in Princeton. He is one of the leading physicists of his generation. His work spans particle physics, string theory, and cosmology. How do you do it all, Nima? And Nima was one of the inaugural winners of the Breakthrough Prize in Fundamental Physics. Next to him, we have Daniel Harlow. He was a postdoctoral fellow at Princeton and Harvard before joining MIT in 2017. He's now an assistant professor in the Center for Theoretical Physics at MIT. He's a winner of our New Horizons in Physics Prize for early career researchers who make important advances. Beside him, we have Daniel Jafferis, who went to Yale at age 14. What took you so long, Daniel? He went on to Rutgers and the Institute for Advanced Study and is currently an associate professor at Harvard, as you do. He's also won this year's New Horizons in Physics Prize. And finally, we have Aaron Wall. He's been a postdoc at UC Santa Barbara and the Institute for Advanced Study and is currently a research associate at Stanford University. He'll be a lecturer at the University of Cambridge in the UK from next year. He is also one of our New Horizons winners. So welcome all of our panelists, please. So I want to start with a sort of real basic question about, and let me throw this to you, Nima, about the nature of time. What exactly is time? And
let's start with the easy one.
Yeah, well, I mean, why not?
Well, time is what stops everything from happening all at once. Well, I mean, time exists in the most obvious way. We've all known about it. There are lots of reasons. We'll get into it presumably at some point later in the discussion why we think time and space might not be as fundamental elements of reality as they obviously seem to be. But to begin with, time certainly exists. It's hard to forget about its existence at any time.
I mean, you say it's hard to forget about its existence, but maybe let me throw this over to you, Daniel Jafferis. It doesn't seem as though physics necessarily prefers one direction in time, and yet our experience of it is one directional.
Right, so I think you referred to the fact that if we evolve the laws of physics backwards, they will look mathematically the same as evolving forwards in time. Up to some caveats, that's true. You have to switch some other things, and then that will be true. But I think part of why we experienced that difference was understood in the 19th century as in terms of the laws of thermodynamics. So in the far past, the configuration had low entropy. It was a very ordered configuration, and the disorder increases into the future. So that's why when you drop eggs, they break, and you don't see them unbreak.
It's a property of macroscopic systems. They're made of tons of particles, and they become more disordered over time.
Right, exactly.
But not just the systems, the initial state as well.
The initial state is special.
Yeah.
And we don't know why the initial
We
state
don't know
was
why.
special.
Yeah, that's
We don't know why.
a confusing cosmological question.
So let's clear up the question, can you travel through time?
We do it all the time.
Doing it right now.
Yeah. Watch is
One
Rather
second.
distressingly so.
yeah.
You know, that,
yeah.
We are traveling through time. Are there ways to travel through time differently than the ordinary ticks of a clock that we normally expect? Aaron, do you want to take that one?
Yeah, so there's, Einstein's theories of relativity say there's two ways to go through time faster. That is, you experience less time than other people would. One is to go very fast, near the speed of light, and the other is to be close to an object with mass that has gravity. So time actually goes at a very, very tiny fraction of less on Earth than it would measured by a clock in outer space. And the most mind-blowing thing about that, I think, is that that's actually why we fall down. It is what causes gravity.
See, now that's not immediately obvious, I think, to most people. The reason we fall down, Nima, is because time.
that manifestation of the curving of this. People often talk about Einstein's ideas about gravity being related to a curvature in space and time using this pretty terrible rubber sheet analogy. It's a pretty terrible rubber sheet. It's a pretty terrible analogy because first, what's making a dimple to begin with is gravity. It's kind of bad for many reasons. But more importantly, it makes you think that the important part of the curvature is in space, whereas really the important part of the curvature is in time. And so that's and absolutely, this curvature in time is responsible for falling. Exactly the effect Aaron was talking about. And the more, maybe the slightly more standard one, which is still pretty mind-blowing, is that if we can definitely visit the future. We can definitely visit the future very, very effectively if we have access to a spaceship that can go very, very close to the speed of light. If I hop on a spaceship and I go at 99.99% of the speed of light for 6 months, and I come back to Earth, then I'll see what the Earth looks like 100 years later, even though I've only been traveling for a year myself. So it's possible to visit the future without any problem, and to visit the future faster without any problem. That's an amazing thing that Einstein taught us. But that's somehow not what people want to talk about when they talk about time travel. They want to undo their mistakes and talk about going backwards in time, which is, I presume, where we're eventually going to get.
Well, yeah, I guess that is the logical next question, which is going forward in time faster than we ordinarily do. That is possible. But going back in time, is it theoretically possible? And what are some of the potential ways that theoretically we think it may be possible?
Well, I have probably a different philosophy on this kind of question than the standard one. So there's a kind of dumb way of going back to the past, which is perfectly consistent with the laws of physics, which is that you could imagine that you yourself are part of some large system that involves everything in the universe. And usually we think that those rules are fixed. But actually, for example, it could be that that's really part of some system which is being simulated by some other laws of physics. So for example, if you think about what's going on inside of a material, like in the topological insulators that were being talked about earlier today, there are laws of physics which are sort of emergent laws of physics. Ultimately, you can derive them from the fundamental ones, but you can also just think about it as a system on its own. And indeed, if we were to build a quantum computer, which is the kind of, I guess will come up probably multiple times tonight, the whole point of having a quantum computer is you have a system where you get to choose the laws of physics. You can evolve using one set of laws, or you can evolve using another set of laws. And in particular, there's a kind of crazy thing you can do, which is you can just pause the simulation so that time stops flowing. And not only that, you can actually then start running the simulation backwards. So you could imagine that you yourself, and people even talk about it, right? We're in Silicon Valley, so we're allowed to talk about things like downloading your brain into a computer and so on. And were you to do that, then you could run the computer forwards and you can run the computer backwards. And after you ran it backwards, you'd be back to where you started. And so that's some kind of time travel.
So
but it's not.
You think it might be possible on some level to run the entire world backwards?
Or at least the part of it involving you. It's hard to run it's hard to imagine that we would have that control over the entire.
It's hard to imagine run anything back in time, but I mean.
That's exactly right, although we can do it with small systems. But the thing is, this isn't really what you want when you talk about time travel time traveling back to the past, because what you really want is that when you get to the past, you still remember the future, even though it hasn't happened yet. And that wouldn't happen if you just ran everything backwards, because when you're running it backwards, you just forget everything that happened, because you just get back to whatever state you were in, before you ran things forward. And the really interesting thing,
that's just a minor hiccup, right?
Well, you make
but it's actually but it's extreme. Right. No, but it's essential, because so you could imagine trying to, arrange to run things backward. If you try to run everything except for you backwards, it's very, very difficult, because the problem is that, as was mentioned by Aaron, right, in cosmology as we currently understand it, entropy is increasing. There's a very strong arrow of time, which is why eggs break and don't reform. And if you imagine doing the time reverse of that, to having a universe where entropy was decreasing, that's allowed. That's a solution of the equations of physics as we understand them. But it's extremely unstable. You make the smallest little perturbation, just even move the location of one atom, and immediately, moving outward at the speed of light from that atom, you'll have a new situation where now within, the future of that atom, entropy is increasing again. And so this thing where you want to run yourself, run everything except for yourself backwards, that's that one small perturbation. And so I would say really the reason why we don't think that time travel is possible is really because of this, the second law of thermodynamics.
It is a bit of a hurdle.
But this raises the question of whether you could do it with gravity instead.
So I know that Aaron Wall and Daniel Jaffers here published a paper that caused some stir about traversable wormholes. So can you tell us about traversable wormholes, and would they allow us potentially to travel back in time in a useful way, where we'd still remember the future, but we'd be back in time?
Right, so a traversable wormhole means a configuration where you can jump into it in one place and come out on the other end somewhere far away. The fact that you can get through it is what makes it traversable. Now, it wasn't clear for a long time whether such configurations of curved space and time are actually possible in the sense that they would obey all of the laws of physics in our universe. And one prerequisite for such a configuration is that there's negative energy in the interior, which sounds very difficult to achieve, or it probably sounded impossible. Now, what we found is that using some subtle quantum effects, this kind of configuration is possible, but it requires a direct interaction between the two ends of the wormhole. So if there was some weird material that had negative energy, then you could make this traversable wormhole and use it, convert it into a time machine by taking one end and appropriately moving it in space-time so that it ended up in the past of the other end. But in the kind of traversable wormholes that actually work, that obey the laws of physics, that doesn't work because it required a direct connection between the two ends.
So you need someone back in the past
Well,
to be working with you. Am I following you?
right, I mean, it means that there's a particular causal relation between the two endpoints of the wormholes, which has to be obeyed in order to support the wormhole, and that disallows one endpoint from being in the past of the other endpoint.
So you don't win by going through. If
Right.
you try to go the long way around, you actually get there faster.
Exactly.
So
it's
the
not a
way
useful.
the way I said this in the paper was that a traversable wormhole is like getting a bank loan. You can get one if you prove to the bank you didn't need it.
Right.
So
So Nima, have you got any other opportunities for us to maybe go back in time?
Well, I mean, I think this whole discussion is, it highlights something really important. There's a sense that, and part of the character of this question is, well, maybe as we learn more things, all kinds of crazy stuff might become possible that today we think is impossible. And 400 years of the history of physics has actually had exactly the opposite direction of progress. As we've learned more and more, we find out mysteriously that more and more things are impossible. There's a, before Einstein, in Newton's world, you could in principle reach out and touch someone arbitrarily far away. So part of the information of the universe was everything that was out there at a given time, and you had access to it. After Einstein came along, there are regions in space right now, and that whole notion of right now even loses its meaning, that we can't have any access to because there's a finite speed it takes for information to get.
It's like your whole future is limited. That we know there are bounds, places you will never go, things you will never interact with.
Absolutely, and when that was true, but Einstein didn't change the fact that if we specified what was going on now everywhere, we could predict what happened in the future everywhere. And then quantum mechanics came along, and it took that away from us. So there's always fewer and fewer things we're allowed to talk about, more and more things that are somehow impossible. And the direction of progress has never been to reverse that and say, oops, we were wrong about that. It turns out to be possible after all. It gets more and more restricted. The silver lining of this is that as more and more things are impossible, the things that are left to talk about turn out to be more and more mysteriously unified with each other. And the sort of consistency of the laws of nature hang by a thread. It's I think, a miracle we don't really understand very well. But especially these principles that we discovered in the early part of the 20th century of Einstein's ideas of even about special relativity and quantum mechanics are almost not obviously compatible with each other at all. They're barely compatible with each other. And one of the interesting things that's actually come up in this whole discussion and the work we're just talking about is an aspect of it, there are other aspects, is it's not as obviously impossible to prohibit the ability to go back in time, just from the structure of the equations, as you might very naively expect. And so you can study situations, maybe Aaron will talk more about it in general relativity, and that was something that goes back to Kurt Gödel in the middle part of the last century, where it's possible to get these so-called the fancy name time travel, closed time-like curves. More recently, people have been investigating the possibility that in completely ordinary physics, things go exactly at the speed of light, not a little faster, not a little slower. If you could go a little faster than the speed of light, that's associated with being able to go back in time. But people have started exploring that it could be that if we incorporate the effect of physics from very, very short distances that we haven't seen yet, that could give you a little kick that could, in principle, push you one way or the other way, to go either a little faster or a little slower than the speed of light. And nothing in the obvious structure of the equations tells you ahead of time that you shouldn't be able to go a little bit faster until you start studying it in a little bit more detail. And then some interesting consistency involving other parts of physics that are not clearly related to these things. Consistency with the principles of quantum mechanics, the fact that probabilities should all add up to 1. This part of this, what I was just referring to, this very, very thin thread that the laws somehow manage to be consistent with each other with, turns out to over and over again forbid this from happening. But the
But
study
just barely.
of how, just barely.
Yeah, that's
That's
what's really
that's
amazing.
what's so
Just
interesting.
barely.
Exactly.
Yeah.
So the study of why we can't send signals back in time turns out to be something interesting and is telling us surprising features about physics that we haven't seen yet.
In that sense, there is a back and forth dynamic it's in physics about this question. It's a little like a joke I once heard where a man is falling out of an airplane. Fortunately, he has a parachute. Unfortunately, the parachute doesn't open. Fortunately, there's a haystack underneath him. Unfortunately, there's a pitchfork in the haystack. Fortunately, he misses the pitchfork. Unfortunately, he misses the haystack. So I don't know which of the two positions you want to call fortunately, unfortunately here, but it's actually important to say this to explain the dynamic of what's going on, because it's not just a simple, straightforward answer, time travel is impossible because of X. The history is more like, it's impossible because of X, but here's a loophole in X, but then the loophole is closed for this other reason, but then what about this situation?
And we keep learning a little bit more about physics we didn't know about before by tracing this question. It's surprising how fruitful it is to think about this.
So as an example, Stephen Hawking proved a theorem that says, roughly speaking, that if you don't start with a time machine in general relativity, you can't build one. But his theorem has some assumptions. One of them is that it's a classical general relativity theorem, which means we aren't taking quantum mechanics into account. And another assumption is that all of the energies are positive. There's no negative energies. Now, we know if we do take quantum mechanics into account, there can be these negative energies, even though they have to be balanced by positive energies somewhere else. So it becomes a more delicate question. So when I was a grad student, I wrote a paper where I argued you could extend it to the quantum level by using another idea of Stephen Hawking's and relating it to the second law, the thermodynamics of event horizons. That if you could go back in time, you'd have in a closed time-like curve, over and over again, you'd have your sort of own personal event horizon. It would violate the second law. So that's an example of this dynamic. On the other hand, in the same paper, I argued this ruled out traversable wormholes, and nobody liked that. And then when I wrote a paper with Dan Jaffers and his grad student, Ping Gao, that there can be traversable wormholes, people were much more excited by that paper.
So people want these traversable wormholes to be real. Is that?
Wouldn't you?
Well, I would like.
Depends if you have friends in Alpha Centauri that you want to talk to,
Yeah.
now.
But if you have enemies in Alpha Centauri, that's...
Right, you don't want to. Indeed.
Right. Well, yeah, it could be a double-edged sword. I mean, do you ever worry about some of the paradoxes of time travel?
Yeah, so I think there's a general, there's a funny thing, that's true, seems to be true in physics and also even in computer science, which are two fields that are just getting closer and closer, which is that there seem to be these sort of fundamental limitations on what we can do, and what Nima was just saying is an example of that, where somehow we don't really know why the laws of physics should have to respect causality, but everything always seems to conspire so that they just barely do. And similarly in computer science, it's kind of embarrassing. We still can't prove that P is not equal to NP. We can't show that computers are problems that you can easily check the solution can't also always be solved easily, which seems obvious. But it's the same kind of thing where every time you have some clever idea about how finally you're going to, show that P equals to NP, it doesn't work, it works only in the cases where it just barely can't be used to show that P equals NP. And so there's this, it kind of gives you this sense that there's some, humility there that, if these things were worked out differently, it would just, everything would be different, right? I mean, what does physics mean? You know, physics means that we take the state of things as we see them now and we try to predict what happens next. You know, that's just somehow every kind of physics. That's what we're trying to do. But if you could violate causality, then that wouldn't be a meaningful question. You know, it wouldn't even, you know, it would be like, you know, just our whole experience of the world is that, you know, we're gradually learning more as we go through time and trying to adapt our views to be consistent with what we've learned, and all that would change. I mean, I don't even know what it would mean or what it would feel like. You know, or whether we could be conscious.
Do you think
in a world with time
do you think it
travel.
would be the kind of thing that as soon as a time travel device were invented, allowing you to go back in time, you would disrupt the flow of all of the events that led you to create that time travel device? Therefore, you couldn't go back in time. Is that even?
No, I don't think so. I mean, there are consistent solutions of general relativity where there's a closed time-like curve, and just somehow everything conspires so that when you get back to the same time, it's all the same as
But
before.
in the general theme of what we're talking
Yeah.
about, one of the things about those solutions is that to do something useful with it is just to go back and stop something terrible from happening, or something you have to add a little perturbation to it, not just this perfect. And they're horrendously unstable to these tiny perturbations. So,
You're right. Yeah.
so this business that the obvious paradoxes will not happen, cannot happen. But what's very interesting over and over again is that it's less obviously forbidden from the get-go than as you might think. And actually, one thing I want to emphasize, since it's been brought up a couple of times, but I want to emphasize how sort of fascinating it is. This question about moving forward in time, the inability to go back and kill your grandmother and so on, these are questions that you could have wondered about. Well, you could have wondered about them 5,000 years ago. We could have wondered about them certainly within the context of classical physics, and people did. When you see the things that's actually making it hard to make these time machines, even classically, something Aaron alluded to, it involves seemingly obvious properties about energy, that you can't make energies negative, they can only be positive, and so on. Then quantum mechanics comes along and allows naively exceptions to these things. And so it's quantum mechanics that opens a whole new world of sort of possible ways you think you might get around this. But over and over again, the interesting correlation that we see is that while quantum mechanics lets you do things that classical physics doesn't let you do, there is a strong correlation between this idea of moving forward in time in classical physics and the idea in quantum mechanics that while the world isn't deterministic, probabilities always have to add up to 1. Okay? And those two ideas are not obviously related to each other ahead of time, but they end up behind the scenes supporting each other in a fascinating way.
Yes,
and I think, I mean, this is maybe, it's not orthodoxy in the field, but I certainly think that this is one of many, many clues that there's a very deep relationship between time, space-time, and quantum mechanics, and that they're somehow behind the scenes more closely tied to each other than they appear.
Well, these days, many people say that entanglement is geometry, right?
Well,
So,
but not just for space, but in time as well.
Let me stop you with
Right.
entanglement is geometry there. And I want to go down the line and just get a quick yes or no. I'm going to ask you to lay your biases out on the table. Do you think that humans will ever create a sort of time machine in the way that most people think of it? What do you think? Yes or no?
I think if you want to get younger, you should talk to the life sciences people. No.
Daniel Jaffris,
Yes,
time travel, yes or no?
I agree. No, we won't have a time machine of that time.
Nope.
Nope.
Depressing.
Is time travel possible? No. Not if you want to go back. And with that, I want to thank all of our panelists, and we have no more time, so we're going to hop off the stage. Thank you so much.